Today we'll continue looking at graphical models, specifically Gaussian mixture models and hidden Markov models, and we'll develop the general expectation maximization algorithm for performing inference on those models. So to review Gaussian mixture models from last time, remember that the setup is that we have some observations from a distribution. So in terms of where to slot this into your existing knowledge, you want to think of this very much like classical statistics, where we're trying to fit a distribution to a collection of data by finding the parameters for the density which best align with the data, in the sense that the likelihood is as large as possible. Except that here, instead of trying to fit a single multivariate Gaussian distribution, we're going to try to fit a sum of multivariate Gaussian distributions. And specifically in this case, we'll just talk about two, although you could have more. And note that this is going to be pretty similar in some ways to something like quadratic discriminant analysis, where maybe the points over here all belong to one class and the points over here all belong to another class, and you fit a Gaussian to each of those classes. This problem is much more challenging though, because you don't get labels. You just get the x1 and x2 values for all of these points, and you have to come up with the choice of which points to fit for each distribution. So we described this with a Bayes-net diagram by positing that each point has a hidden variable, which we called z, as well as the observed x vector, which includes both x1 and x2. So z is going to be a Bernoulli with parameter alpha, and the conditional distribution of x given z is going to be a normal distribution with a mean and covariance that depend on z. And again, this z random variable, it's part of the setup of the model, but it's not a value we're ever going to get to observe. So we're going to have to use techniques that account for the fact that we won't get training data with the z value revealed. So the idea is maybe the z value for this point is equal to 1, and the z value for this point, let's say, is equal to 1. Z value of this point would probably be 0, indicating that in this sampling procedure, it was ultimately drawn from the normal distribution with mean mu 0 and covariance sigma 0. And in the middle, we can make much less confident guesses, like maybe this point happens to be z equals 1, even though it looks more in the 0 cluster, and so on. So if you want, you can think of the z's like labels in a classification problem, except that they get completely scrubbed before we get to look at the data. And since we don't get to see the z's, we associate with each point the conditional expectation of its z value, given where it's located. We call that value pi. So for example, this point might have its pi value up at like 0.999, because the purple density is much higher than the green density at that point. Same idea with this one. The pi value at this point likewise would be very close to 0, because it's very likely that that point corresponded to z equals 0. And a point more in the middle might be much more ambiguous. That point might have its expected z value around 0.4 or something like that. So note that the pi values and the model parameters, that is to say alpha together with the mu's and the sigmas, have kind of a symbiotic relationship. If you freeze the model parameters, then you can compute the pi values for each point. But on the other hand, the pi values inform the model parameters. They say for each point how green or purple it is, and allow the green distribution and the purple distribution to fit the greener and purpler points, as well as choosing how much mass alpha to apportion to the purple class versus the 1 minus alpha mass apportioned to the green class. So the algorithm we described for coming up with these pi values and these model parameters jointly, we called expectation maximization. So we start with some arbitrary choice of theta, which is just a packaging of all the parameters in the model. And then repeatedly we perform two steps. We compute the pi values with respect to our current theta. So assuming the model parameters as they are with our current guess, we compute the conditional expectation for each point of its z value. That's just going to be the amount of purple density at that point divided by purple plus green density. So that means choosing alpha to be the average amount of purpleness in the diagram. In other words, the sum of all the pi values divided by n. And choosing mu1 to be the pi-weighted mean of the points. So we just weight each point by its purpleness and compute a new mean for the purple distribution. Likewise, sigma 1 will be a pi-weighted covariance matrix of the points. Mu 0 will be a 1 minus pi weighted mean, so each point gets weighted based on its greenness, and so on. So in action, that might look something like this. We start with some initial guess, which isn't very good, and then we weight all the points. So like these points would get a pretty high greenness score. In other words, their pi values would be close to 0, and these points would get a pretty high purpleness score, in other words, their pi values would be closer to 1. Ones in the middle would be closer to a half. And then we reset our alpha according to the overall amount of purpleness, which I'm not really illustrating in the diagram. So here that would probably be less than a half because there are more points that get assigned a high greenness score, in other words, a low conditional expectation of z. And then mu1 gets set to the pi-weighted center, in other words, the purpleness weighted center of the points. So here all the points contribute to this computation, but in proportion to their conditional probability of having been purple under the previous parameter assumptions. And then same for sigma 1 and same for the green distribution. And what we'll see in this case is that based on where we started, we actually are going to lock into a final distribution that's pretty close to this one. Because now these points are super green. The green distribution is only going to shift a little bit to accommodate those points on the next step. These points are really purple. And so the model is going to be pretty happy with this particular configuration, even though perhaps overall this configuration with a suitable alpha might have had an overall higher likelihood. So this is not a convex optimization problem, and it's possible to get stuck in local maxima away from the global maximum. So this setup was highly driven by the details of the problem, and it's far from clear if you have a more complex Bayes-net diagram what the appropriate generalization here is. So let's alter the way we've described this algorithm to make it general. So generalizing the first step, we get something that's transparently the same in this case. Compute the conditional distribution of z given x with respect to our current theta values. That's exactly what we had decided to do in this Gaussian mixture model example. However, the second one is going to look different initially, and it's going to take a while for us to close the loop. We're going to work out the likelihood over x and z. So we're going to pretend that we know the z values as well as the x values of each observed point. Except that since we don't, we're going to leave the z values as variables. So we'll get an expression involving some x values, which we can substitute because we know them, and some z values, which are variables, which we don't know. And then we take the expectation of the log likelihood with respect to the conditional distribution over the z's. So in other words, since we don't know the z's, we treat them as random variables with an appropriate distribution given the data that we do observe, and then integrate out that randomness by computing the expectation. And lastly, we're going to choose parameters that maximize this expected log likelihood. So the first problem asks us to show that this algorithm generalizes the one we just described for the Gaussian mixture model. In other words, show that it produces the same results when applied to the Gaussian mixture model. So to do that, we need to carry out this program we just described. So step one was to compute the likelihood over z and x. So for each particular point, let's say this one with a z equals 0 value, the likelihood that it contributes is just the density at that point. So the density that the model assigns to this particular z comma x pair is 1 minus alpha, the probability that the point was going to be green in the first place, times the green density value there. If the point had been purple, it would have contributed a factor alpha f1 of x to the likelihood. F1 is shorthand for Gaussian density with mean mu1 and covariance sigma 1, and likewise F0 is shorthand for a Gaussian density with mean mu0 and covariance sigma 0. And we can do this little trick to say if z is 1, return this purple term, and if z is 0, return this green term by multiplying the first factor by z and the second factor by 1 minus z, and then adding the results. So that's the contribution to the likelihood for a single point. The overall likelihood is the product of all the contributions from all the points. So for each point, we'll identify its z value as zi and its x value as xi, and we'll just be multiplying all of these factors. Each factor is either this value or this value, depending on whether the point is green or purple. So then the log likelihood is the log of this product, and the log of a product is equal to a sum of logs. And now we can say the expected log likelihood will be the expectation of this sum, which is equal to the sum of the expectations. So we just need to consider for each point I, what's the expectation of this expression? And there are only two possible values for zi. So we can use the formula for expectation, which says compute each possible value, multiply it by the probability that value is realized, and add up the results. So one possible value would correspond to zi equals 1. If zi equals 1, we just get this factor. And that has probability pi 1. because remember we're computing this expectation with respect to the conditional distribution of z given x. And under the conditional distribution of z given x, the probability that z is equal to 1 is just pi I. That was the definition of the variable pi. Likewise, if z is equal to 0, we pick up this second term, which has probability 1 minus pi I. So this is our expected log likelihood, which is often called Q of theta. And notice that the theta comes in here because it includes alpha, which shows up here and here, and it includes mu1, sigma 1, and mu0, sigma 0, which show up in these densities f1 and f0. So if we want to find a value of alpha that maximizes Q, we can differentiate with respect to alpha and set the result equal to 0. For each term here, we get pi I log of alpha plus 1 minus pi I log of 1 minus alpha, plus some other stuff that doesn't involve alpha. So pi I log of f1 of xi, and similarly for this log of f0 term. But if we differentiate this expression with respect to alpha, we get the sum of pi I over alpha minus 1 minus pi I over 1 minus alpha is equal to 0. And alpha works out to the average of the pi's, which is exactly what we started with. That's the overall amount of purpleness given our current parameter values and our observed values of x. Likewise, when we go to maximize this sum, this is a pi-weighted log likelihood for the problem of fitting a Gaussian density to the points. And we're going to skip the details here because it's a little computationally messy, but the maximum likelihood estimator for a multivariate normal distribution without the weights is just the sample mean and sample covariance. And that's exactly what comes out here, except instead of computing the ordinary sample mean and the ordinary sample covariance, we'll end up computing weighted versions of those. So it all worked out. This general algorithm we described produces the same results in the Gaussian mixture case that we worked out intuitively, but it can apply to any Bayes net where we have some variables z which are hidden and other variables x which are observed, and we're trying to come up with parameters for the model that fit the collection of observed data. So let's look at another common Bayes net. This one is called the hidden Markov model. So the idea is that we have a Markov chain. For example, this one where we have two states, 0 and 1, and the transition probabilities are 80% to 1 and 20% to the loop when you're in state 0, and 1/3 to the loop and 2/3 back to state 0 when you're in state 1. So this is our Markov chain, and it's going to contribute the hidden variable z in this problem, hence hidden Markov. So here we're generating an example sequence of observations from the Markov chain z. So we're defining this offset array. So that's an array where the starting index of each axis can be something other than 1. So here we're going to want to talk about a Markov chain whose states are 0 and 1 rather than 1 and 2. We define an offset array with indices 0 and 1 for both axes. So typically our row and column labels would be 1 and 2, and here we're setting them up to be 0 and 1. So we'll generate 100 observations, and we'll start, let's say, in state 0, although initializing the random state is something you could do if you want. And then we'll take a bunch of steps. We'll set our current state to be where we are now, so that's the end of our current z vector. And then we'll push onto our z vector our new state, which is obtained as 0 or 1 randomly, depending on the value of the corresponding entry of the transition matrix. So this question mark and colon, it's called a ternary conditional, and it's just saying check this thing. If it's true, return this first value I gave you. If it's false, return this second one. That gets pushed onto the vector. We repeat n times, and we get our full Markov chain z, and this is what it looks like. So the idea of a hidden Markov model is that there's some extra randomness. So each state is going to get corrupted in some way that depends on what that state is. One simple form of corruption would be to just add a standard normal random variable to each z. So it would look something like this. This first one was a 0, but it had a negative 1.39 added to it when this extra randomness came in. So we can visualize this by plotting both of them. So the blue plot is the original sequence of zeros and ones, and then the red plot is the actual observed sequence. And the goal of what we'll be trying to do here is collect these observed red values and try to reverse engineer a set of model parameters. So in other words, the transition matrix, together with any parameters dictating the conditional distribution of each x given its corresponding z, that fits this data well. So problem 2 says draw a Bayes-net diagram illustrating the relationship between the x's and the z's. So the first random variable we draw is z1. Then once we know z1, we can observe z2, and its distribution conditioned on z1 will depend on z1. Once we've observed z1 and z2, we can observe z3, and in principle, its conditional distribution given these first two random variables might depend on both random variables. But since we're talking about a Markov chain, it's only going to depend on z2. Once we've sampled all the z values, we can start sampling the x values, and x1, which is a corruption of z1, will have its conditional distribution given all of these z's depending only on z1. Likewise, each of the other x's, even conditioned on everything else in the diagram, will only actually depend on the z that it corresponds to. And actually, typically the assumption that's made for a hidden Markov model is slightly stronger than what's communicated in the diagram, which is that all of these conditional distributions are the same as each other. In other words, the conditional distribution of z3 given each possible value of z2 is the same as the conditional distribution of z2 given each possible value of z1, and so on. So that's called time homogeneity, which can be dropped but is typically assumed. Likewise, we assume that the way that each x is generated from a corresponding z is the same for each time step. So we're going to talk in much more detail about how to apply expectation maximization to a hidden Markov model next time. But in problem 3, we'll start building some intuition for that now. So here's an observation of x where we haven't yet observed z. We can get ourselves ready to see what z actually was here. So this first value, negative 0.96, suggests that maybe the initial z value is 0. Because if it were 1, then the random noise that got added in that position would have had to be negative 1.96, which has a lower likelihood than just negative 0.96. So we're going to conjecture that the first one is 0. Likewise, the second one seems more likely to be a 1. The third one seems pretty borderline. And in general, we're more likely to be in state 1 than state 0 based on the Markov chain. Because if you're at 0, you're more likely to move at 1 than to stay, and if you're at 1, you're more likely to stay at 1 than to move. For this third one, let's maybe let that consideration take precedence and predict a value of 1. And finally, in this last position, we'll predict a value of 0 since a noise value of negative 2.68 is relatively unlikely. So we observe our z values and we see we got 0, 0, 1, 0. So we guessed incorrectly about the 1 in this position. And there's two things to say about that. One is that the conditional distribution of z given x is still random. It will not be possible in general to make a perfect guess based on what we see. But also, we could have done this in a smarter way. We didn't consider the joint relationship of all the x's, and we really should have done that. So the answer to B is yes, it would have been helpful to consider the x values in all the positions when we were making the prediction of each of the corresponding z values. And in part C, we're asked to come up with an example where it's really clear that we should be doing that. And I think the easiest way to see this is just choose extreme parameters for the Markov chain. Let's build a Markov chain where instead of having these relatively modest values, the chain is extremely likely to do something consistent. For example, what if both switching transition probabilities are 0.001 and both staying probabilities are 0.999? So in this case, we expect to see values which are closer on average to 0 for a long stretch, and then see values which are closer to 1 on average for a long stretch, because the underlying state is sticking at 0 for a long time or sticking at 1 for a long time. So suppose, for example, we see a graph like this. So these are our observed x's, and we're trying to figure out what the z's are. If we're just making each guess, ignoring everything else that's happening, then the decision boundary will be a half. Everything above a half, we guess it's a 1. Everything below, we guess it's a 0. But if we do that in this case, then we end up with this extra hump. So we get 3 switches here, a 0 to 1, and then a 1 to 0, and then another 0 to 1 here. And that's much less likely than the possibility that we stayed at 0 for this step and just happened to have an exceptionally large error here. It's not terribly unlikely that the noise that got added at that point was 1.2 or whatever it looks like here. It's much less likely that we spent 2 extra expensive transitions to reach up to this 1.2 value. So the point of this exercise is to recognize that there's a subtle trade-off going on, involving the randomness connecting each state to the next one, and the randomness connecting each hidden state to the resulting observed state. So in summary, expectation maximization can be applied to any situation where we have a model for some observed data, which involves some specified relationships with some unobserved hidden variables, which we call z. And given a collection of observed x values, we'll start at some choice for this collection of model parameters, theta, and then we'll repeatedly alternate the following two steps. Find the conditional distribution of the z's given the observed x's. And then second, we maximize the expected log likelihood of the x's and z's. So in other words, we work out the log likelihood with respect to the x's and z's, pretending that we've observed both the x's and z's. But since we don't know the z's, we leave them as variables. And then we take an expectation by treating those z's as random variables whose distribution is given by the conditional distribution found in part 1. So this expectation is with respect to the conditional distribution of the z's given the observed x's. And lastly, a hidden Markov model is a Markov chain together with another collection of random variables, one for each time step of the Markov chain, which represents an altered or corrupted representation of the actual state of the Markov chain at that time. So the conditional distribution of x given its z can be whatever conditional distribution, but it does have to be the same for each time step. And the kinds of questions you can explore for a hidden Markov model include parameter inference like we did for the Gaussian mixture model, where you're trying to estimate the parameters in this transition matrix, together with any parameters in the conditional distribution that dictates the corruption of each state. And the other goal which we'll encounter along the way is to infer z based on the observed x's. So to say something about what the conditional distribution of the sequence of z states is given the observed x values.